Welcome to Ask and Learn.
Let's use the ratio test to determine whether the series converges. So let's denote this by an. Then the ratio test requires us to look at the limit n goes to infinity, absolute value an plus 1 over an. So let's go ahead and write that out carefully. So we'll have our numerator is 10 to the n plus 1, and then n plus, so we'll have n plus 1 here instead of n, and then we still add 1 to that because of this 1 over here. And then we'll have 4 to replace n with n plus 1, and then still add in that other 1 over here because of that one. So this, everything we've written so far is just our numerator, an plus 1. And now we'll divide that by an, which is just our formula in the beginning. So before we cancel, let's just go ahead and rewrite this. We'll flip the blue fraction and then we'll just multiply it to the numerator. And you can see here that all the terms are positive because n is bigger than or equal to 1. So you can drop the absolute values here. Then go ahead and simplify those exponents. And now we'll start canceling what we can. We see that we could cancel the denominator there, the 10 to the n, with this n up here. So that'll just give us a 10 in the numerator. And then looking at these terms over here, if we cancel the 2n plus 1, we'll just have 2 in the exponent left over in the denominator. And then we still have n plus 1 over n plus 2. And as we take the limit of this expression here, that limit just approaches 1. You can do L'Hopital's rule if you need to see that this limit goes to 1. So when we take the limit, we get 10 over 16 times 1, which is 5 over 8, and that's less than 1. So we conclude that the series converges by the ratio test. By, and then the ratio test. And that's our final answer.